new section, 2.7. And in this section, we will not see any applications, but this is a very important section where we will learn new rules, how to calculate the derivatives. But let me recall, first of all, some notations from section 2.4, where we introduced delta y and delta x. And so suppose you have y that is equal to f of x, then if you have delta x, that gives you the change in y, which is f of x plus delta x minus f of x. And now let's try to calculate the derivative of the product. So this kind of small topic, product rule. So suppose you have a function which is the product of two other functions, y u of x times v of x, where u and v are differentiable functions. And suppose we want to calculate the derivative of such function. And in order to do that, let's do our 3 steps, or 4 steps. And what is the change in y? Change in y comes from 2 places. First, you can change u. So u is changing, and it becomes u plus delta u. Or it can be change in v, which is v plus delta v. And we should subtract the initial value, which is u times v. Right? Again, if you compare this line with the one that I wrote, so you have function, then you evaluate at the new point x plus delta x, but that gives you this change in x happens in both functions u and v. So you get change in u and change in v, and that's what is written here. So this is first step. Second step, not the second, but let's simplify it firstly. And as we discussed, usually we'll have cancellation, and that happens here as well. So let's multiply the parentheses, and I'll get u times v plus u times delta v plus delta u times v, and plus delta u times delta v, and minus uv. And indeed, there is a cancellation of u and times v. And second step is to consider the ratio delta y over delta x. And I will divide term by term. So I'll get u times delta v divided by delta x. And for some reason, I divide, since the product, I can divide just one factor. And for some reason, I divide the one that has change, that has delta sign in it. So I get delta u over delta x times v, and plus, say, delta u times delta v over delta x. This is our second step. And the last step was to calculate the corresponding limit. Limit when delta x goes to 0 of this ratio. And again, I have the sum of several functions, and because of the property of the limit, limit of the sum is the same as sum of the limits. So I get limit of the first term, u times delta v over delta x, plus limit of the second term, okay, times v, and plus the limit of the last term. Delta u times delta v divided by delta x. And again, then I use u doesn't depend on delta x, so it's just u of x, so I can put it in front of the limit. And then I will get limit of delta v over delta x, which is just by the definition, the derivative of function v. So I get u times, if you use the following notation, dv over dx. And the same story happens here. V doesn't depend on delta x, so I can consider just this limit, and this is by the definition derivative of u. So it's du over dx times v, and plus this one, and I will show you that it is going to be 0. And how to show that? So let's see. Basically, in some sense, why it's going to be 0, because you have two deltas in the numerator and just one delta in the denominator. So it's not rigorous again, but in some sense, this is true. So what is delta u? Delta u is u of x plus delta x minus u of x, right? And then the limit of delta u when delta x goes to 0 is equal to the corresponding limit. And so it's u of x plus delta x minus u of x divided by delta x. Oh, sorry, not divided, but just this. But then I indeed can divide and multiply by delta x. Let's divide by delta x and multiply by delta x. But by the definition, this, again, I can use the property of the limit, since this limit exists. And this is, again, by the definition, just the derivative of u at point x times limit of delta x when delta x goes to 0. And this is, but this gives me just u prime of x times 0, which is 0. Of course, in some cases, when my u is not differentiable, something like 1 over x, a derivative at 0, we have seen that it has some problems, and in fact it's infinity. Then you might have here something like infinity times 0. But at the beginning, we discussed that functions u and v are differentiable. Differentiable means it's differentiable everywhere for all real values of x. Then we have here no problems. It's some finite number u prime of x times 0, which is 0. But this is kind of only part of this limit, because then what I have, and then let's consider the limit that I'm interested in, which is delta u times delta v over delta x when delta x goes to 0. But again, as we discussed, we can write it down as a product of two limits of delta u times limit of delta v divided by delta x, and recall that I can do that if I know that these two limits exist. And I know that because I just calculated that this limit is equal to 0, while this limit, again, because v is differentiable, is equal to v prime at point x. And by the same reason, I got that it is 0. And that proved that this limit is in fact 0. Okay, and moreover, some remark that from this, what we have shown, if u is differentiable, then we had that limit of delta u when delta x goes to 0 is 0, right? That was our first step here. And what does it mean? It means exactly that u is continuous. It's one of the definition of the continuous function. So that means that if the function is differentiable, then automatically it is continuous. Other way around, it's not true because, say, and there is kind of first remark. So differentiable implies continuous. But it's not true other way around. So we so this is not always true. And for example, counterexample, y equals absolute value of x. We have seen you can prove that this function is continuous, and basically you can see it from its graph. But as we discussed, that it has problem at 0 because derivative it has problem at 0 because left-hand side limit and right-hand side limit are different. So it's not differentiable x equals 0. Again, you can think about differentiable functions as a smooth function. So some that has form like that. But when you have some corners, like you have in this example, this is not. It's not differentiable. It's continuous because the line is continuous, the graph is continuous, but it's not very smooth. Okay, that was small comment, but what is the summary? The summary is the following, that we got the product rule. So remember that we started with y, which is u times v, and we found that y prime is du over dx times v plus plus u times dv over dx. So what is the product rule? It says that if you substitute what is the derivative d over dx of the product, which is y, is equal to derivative of the first component, first multiplier, times second function plus first function times the derivative of the second function. Okay, and this is our first rule. And from this rule, we can obtain another rule, which is called quotient rule. And the quotient rule is, of course, for quotients. So derivative of the quotient is equal to kind of complicated formula, v du over dx minus u dx over dv divided by v squared. But before proving that, let me formulate the product rule slightly more compact. So using the just prime notations, so uv prime is equal to u prime times v plus u times v prime. This is more complex rule, and probably it's easier to recall it. To remember it. So what happens, you have prime, and then it goes to the first function plus when the prime goes to the second function. And then quotient rule can be also written in the following form. So you have u over v prime, which is v times, maybe for me it's better to write it in this way, u prime times v minus u times v prime divided by v squared. Okay. So for me, it's easier to remember rules with primes. I mean, it looks better from my point of view. Okay, but let's prove it. Let's prove it. It's not very complicated since we already know the product rule. So suppose we have a function, let's call it w, which is u over v. But that means that u is equal to v times w. And let's calculate the derivative of u instead of derivative of w. Derivative of u, because we know what is the derivative of the product. And I think it's, again, I am using prime notation instead of dv over dx or something like that, because it's more compact. You can look at the different notation in the textbook. So again, how it works. First, I differentiate first function and multiply by the second, plus first function times the derivative of the second one. But now, what we are interested in fact, we are interested in the derivative of w. That was our initial problem. So let's express it. That means that v w prime thus will be u prime minus v prime times w divided by v from this equation, right? But what is w? So it's u prime minus v prime times w, which is u over v, and divide by v. But then let's multiply numerator and denominator by v, so get rid of one fraction in the numerator, and then I'll get u prime times v minus v prime times u divided by v squared, and that's what I wanted, because v prime is again what it is, the ratio of u and v. And again, you can switch back to the notations with differentials. Du d over dx of u over v is equal to d over dx of u times v minus d over dx of v times u divided by v squared. So we know how to differentiate the ratio now. And let's apply what we learned in a few examples. So suppose you have a function y, which is x cubed plus 2x squared minus 3x times x to the power 4 or 2 minus 4x. One way to find the derivative is straightforward. You first multiply these two multiple factors, and then you'll get the polynomial of the 5th degree, and then you differentiate. So one way is this. Y is equal to x to the power 5 minus 4x to the power 4 plus 2x to the power 4 minus 8x to the power 3, and so on. And then differentiate. But we already learned what to do if you have a product. So another way, I mean, sometimes this straightforward way is also okay, because then you don't need to think what you need to differentiate. You just get the polynomial and then differentiate the polynomial. So if you're not confident with the product rule, maybe this is the best way for you. But let's apply our rule. So product rule. So again, y. Let me rewrite it one more time. So it is x cubed plus 2 x squared minus 3x x squared minus 4x. So I get the product of two functions. First function is this one, and second is this one. And again, I'm interested in the derivative of u, y, which is derivative of u times v, which is, again, let me repeat this rule, u times v prime. So that means that derivative of y thus will be derivative of u, which is this, 2x squared minus 3x prime times v, which is x squared minus 4x, plus first function multiplied by the derivative of the second one. And again, we got derivative of the polynomial. And so say first one will be 3x squared plus 4x minus 3 times x squared minus 4x and plus, so I just rewrite this, the first function, and then calculate the derivative of the second, which is 2x minus 4. Okay. And this is the answer. Basically, you don't need to do nothing more, because that is fine. Of course, you can open the parentheses again and then simplify, but I will stop here. And that was our first example. And the second example is more complicated slightly. So it's the ratio of two polynomials, so rational function x cubed minus 3x over x plus 1. Again, we have the ratio of two functions. And so y prime will be u prime times v minus v prime times u over, or maybe, and it is better to write it like that, divided by v squared. Yes, common mistake is that the order, sometimes you write it in the not in the right order, or sometimes you forgot that here is minus. So it looks like the how to say, it looks like the rule, the product rule in the numerator but unfortunately there is minus instead of plus. Yes, and in some sense it is a product rule for the functions u times 1 over v. But derivative of 1 over v is 1 minus 1 over v squared, and this minus changes the sign. But this is small comment, you don't need to think about it. Once you get the formula and you remember it. So let's apply it. So let me separate it and calculate u prime first. So this is the same as the prime of this function. And again, it's just polynomial, so 3x squared minus 3, while derivative of v will be derivative of x plus 1, which is just 1. And then let's plug it to the formula. So y prime thus will be 3x squared minus 3 times v, which is x plus 1, minus x cubed minus 3x, which is u, times v prime, which is 1, divided by x plus 1 squared. And again, this is the answer. You can simplify it if you wish and get that it is equal to 2x cubed plus 3x squared minus 3. I skip this calculation because I think you know how to multiply and simplify polynomials. So you can write down in the following way. But again, even on this step, it is totally okay. But sometimes the problem says not only to find the derivative, but simplify it as well. That was our, so we have learned 2 rules, and let's do one more rule, which is called generalized power rule. So we know what happens with the following function, y equals x to the power n. We have learned that y prime is equal to derivative of x to the power n prime n times x to the power n minus 1. But where n is positive integer. But what what happens if we have something like y equals, say, x squared minus 3x plus 2 to the power 7, and we want to differentiate this function? So we see that it is some function to the power 7. So it's not exactly x to the power 7, but some function to the power 7. And for such problem, we can develop the following formula. And the formula is called generalized again. Generalized power rule. And it says this, the following, that if you have a function u of x, then the derivative of the power of that function will be n times, so it looks like the power rule for just x, but then you need to multiply by the derivative of u itself. Yes, in fact, it's true not for integer n, but it's true for all rational n. And that will is exercise from the next section, but we'll prove only for the integers, and in fact you can prove it that it works for any rational n. So n can be represented as a fraction p over q. And this is generalized power rule. So let's prove it. So suppose we have then so y is u to the power n. Then first step is to calculate delta y, and that will be u plus delta u to the power n. And as we have seen when we try to find the derivative of the power, so when we were proving power rule, then we applied the binomial coefficients and binomial theorem to calculate such power, and the answer was like this. It was u to the power n plus u to the power n minus 1 delta u with coefficient n plus n times n minus 1 over 2 u to the power n minus 2 delta u square plus some term that contains delta u cubed, delta u to the power 4, and so on, plus delta u to the power n. That was, oh, sorry, I did a mistake, in fact, because delta y is the value at new point minus the value of the initial point, so minus un. So that gives me the first term and minus un. And again, there is a cancellation of un here. And so I get long expression. And in the same way as we did when we developed a power rule, next step is to consider delta y over delta x. And again, I will divide it term by term. So I'll get n times u to the power n minus 1. Then here, before I had delta x over, before, well, for y equals x to the power n, here was delta x over delta x, and that was 1. But now I have delta u, some function, and that's the important difference. But nevertheless, then I'll get plus n minus 1 over 2 u to the power n minus 2, and delta u square I'll write divided by delta x, I'll write in the following way: delta u over delta x times delta u, and plus many other terms, plus delta u. So delta u to the power n I will write as delta u over delta x times delta u to the power n minus 1. Okay, so I just divide whole expression that I obtained here by delta x. So I can, since it's a sum, I can divide just term by term. And then write it in such way. Delta u n minus 1. But then I need to consider the limit delta y over delta x when delta x goes to 0. And that will be what? Again, limit of the sum is sum of the limits. Limit n u n minus 1 delta u over delta x plus, okay, let me write it on the new line, plus limit n minus 1 divided by 2 un minus 2 delta u over delta x times delta u plus so on, plus limit delta x goes to 0 and un minus 1, oh no, copying, delta u over delta x times delta u power n minus 1. And what happens? Again, this doesn't depend on delta x, so I can put it outside of the limit. And what I'll get, limit of the delta u divided by delta x, which is by the definition. So first term gives me n times u to the power n minus 1 times derivative of u. Then what happens with the next one? Again, whole this expression doesn't depend on delta x, so I can put it in front. So I get n minus 1 divided by 2 un minus 2, and then I'll get limit delta u over delta x times delta u. But this is the same as we just discussed for the product rule. We have seen such expression delta u times delta v over delta x, and we proved that it's 0. The same story happens here, because what you get this is u prime times delta times limit of delta u when delta x goes to 0. But since delta u is differentiable, we have shown that this goes to 0. So I have u prime times 0. And the same story happens with all terms here, where I put dots, because you'll have u prime times delta u to the power 2. Next term will be delta u to the power 2, which still goes to 0. Then delta u to the power 3, that goes to 0. And the same story with the last term, because again you have this times limit of delta u to the power n minus 1. This is u prime, and it's finite because u is differentiable. And this is 0 by the same reasons. Because again, you can write it even using the property of the limit. You can write as limit of delta u to the power n minus 1. Delta x goes to 0. But that what we discussed is 0. So 0 to the power n minus 1 is still 0. Okay, so what is the conclusion? The conclusion is all other terms except the first one goes to 0. And so I get that everything is equal to n times u n minus 1 times derivative of u. And that's what I needed. And again, this proof works only for integer n, because we have used the binomial theorem when we were proving that. And there is no binomial theorem for the rational numbers n. But still, you can prove, and that's what we'll discuss it, but it will follow from the next section. Let's go further. And so we can answer what happens with this function x squared derivative of x squared minus 3x plus 7 to the power 7 d over dx. So this is my u, and this is my n. So by the generalized power rule, I get that it is And again, let me write it. U to the power n derivative is equal to n times un minus 1 times the derivative of u. So it is x squared minus 3x plus 7. Thus will be 7 times the same function, but to the power which is 1 less. So 6 times the derivative of that function itself. So the last step is to calculate the derivative of the polynomial, which is not very complicated. So it is 2x minus 3. So yeah, don't forget about this last step. This is not the final answer. You need to differentiate the function, find the derivative of it. But as I said, you can also apply that generalized rule to the powers which are rational numbers. So for example, y is equal to square root of x squared plus 1. And what is y prime? First of all, you can write square root as the rational power, which is 1/2, right? And then again, by the generalized power rule, y prime thus will be n. So this is again my u, and this is my n. So it's n, which is 1/2, times u to the power, which is 1 less, x squared plus 1, to the power 1/2 minus 1, times the derivative of u. And so I get 1/2 x squared plus 1 to the power minus 1/2 times 2x. And then you can write it in terms of square roots, because what is x squared plus 1 to the power minus 1/2? This is the same as x squared plus 1 to the power 1/2, and then to the power minus 1, which is square root of x squared plus 1 to the power minus 1. So, I mean, I just write it as many details as I can. That's what you should do during your homework. So it's 1/2. So numerator is 2x, and square root comes to the denominator. This is almost the final answer, because now you see the cancellation. 2. And the final answer is x over square root of x squared plus 1. Okay. So the first steps, maybe it's better to write down first u prime. So just create some kind of table. What is u, then what is u prime, and what is n. And the same for the product rule. If you have u times v, it's better to write what is u, what is v, what is u prime, what is v prime, and then just substitute to the rule. But once you get used to that, you will do it automatically. Okay. And it turns out that the generalized power rule is a special rule of what is called chain rule, which involves composition of functions. So recall, if you have two functions, continuous, or in our case, since we want to differentiate them, differentiable, and let's consider f composed with g, composition of two functions, which is just f evaluated at the point g of x. And the question is, what if y is equal to composition? of two functions, what is the derivative of that? And the answer is the following, and it's called chain rule. So how to write it down? There is one way in the textbook that I don't like, but I'll write it in the following way. F of g of x derivative is equal to derivative of the outer function f prime evaluated at g of x times derivative of the inside function g prime of x, or how to say, or in other words, if you denote, if your g of x is, say, u, then you can write down in the following way, that's d over dx of f composition with g is equal to df over du times du over dx. Maybe it's better. Yeah, this is better. So you know that f of u, which is also function of x, then it's derivative of f with respect to u times derivative of u with respect to dx. And that's one of the reasons why you call it a chain rule, because you see it connects here. So in some sense you want to cancel it, and that's what you will get, df over dx. But again, you should think about the this symbol as just the symbol for the derivative. So it's one symbol. It's not the ratio of two at this moment. We'll discuss it later when we'll discuss differentials. But so far, you should think about this as one symbol. So you cannot cancel du. In some sense you can, and in sense of the chain rule. That's what we just discussed. Okay, maybe it looks complicated again at the first glance, but again, it's just the time and experience when you'll get used to that. So let's prove it, and you will see. Let's see. Just thinking how to write it. Maybe better. Yeah, let me slightly modify. d of g of x, that's what we want to calculate, is equal to d over dx of f of u. If you introduced u as g of x. I mean, it's just, again, the matter of notation, but you should decide which way you prefer. Okay, but let's prove it. So you have y, again, which is f of g of x, or which is f of u. And again, what is the derivative of y with respect to dx? It is limit when delta x goes to 0. So even don't need to write the 4 steps because it will be almost straightforward. Delta y over delta x, limit delta x goes to 0, and I will delta y divided by delta u times delta u divided by delta x. So why I cannot stop here? Because delta u, sorry, why I cannot stop on the first equality? Because here delta y is not that simple as before. Before we have, so what is delta y? It's y of x plus delta x minus y of x. But then what you need to do, you need to plug it. So it's f of g of x plus delta x minus f of g of x. And you see that delta x is sitting inside another function. So it's not quite simple to understand what is delta y divided by delta x here. And instead of that, we'll use this trick. So we'll multiply and divide by delta y, or delta u, sorry. So it's tricky. And then everything becomes easy because what you get, because it's a product, I can apply limit of the product is the product of the limits, and times limit of delta u over delta x when delta x goes to 0. But another trick here is that since u is differentiable, that's what we started, that means that it is u is continuous. But that means that when delta x goes to 0, it's equivalent to delta u goes to 0. And so I can, instead of writing here delta x goes to 0, I can write down delta u goes to 0. And that's what I will do. So first limit, I will write limit when delta u goes to 0. It's better to write it like that. Delta u goes to 0, and delta y over delta u times limit of delta x goes to 0, delta u over delta x. And that's it, because this gives me the definition of the derivative of y with respect to u, while this gives me the definition of du over dx. And again, my y is the same as f. How I wrote it, df over du. Yes. Or again, I think how third way to write it down, that derivative of y is equal to derivative of y with respect to u, which is g, times du over dx. That's what we obtained here. But again, these are all equivalent forms, just the matter of notation. You can prove now generalized power rule by just one line, because u of, say, x to the power, to indicate this some function of x. Because what we have composition of two functions. First function f is x to the power n, and second function is our u of x, right? Then composition of two functions will be u of x to the power n. So indeed, the power of some function is just the composition of two functions. And that means that derivative of f composed with g, which is the same as what we did, df over du times du over dx. And so what you should think, you should just differentiate. So derivative of f will be, what is the derivative of x? How to say, yeah, better to say it like that. Again, this f is function of u. So it's u, what is f of u? F of u will be u to the power n. And then df over du will be u to the power, just the usual power rule, u to the power n minus 1. So I get here n times u n minus 1 times derivative of u, which is derivative of u. And this is our generalized power rule. Okay, so let's practice more and say, consider this, x squared minus 1, no, minus 2x, okay, whatever. And let's do third root. Come on. Third root of x squared minus 2x. And the question is to find the derivative. Okay, it's not very good. So first, what I can do, I see that it's product of two functions. So first I can apply the product rule. So first, y prime is u prime times v plus u v prime. So u prime is just 1 because the derivative of x is 1. And then v prime, okay, let me rewrite it in that way. So I get third root of x squared minus 2x plus u, which is x times the derivative of this third root. And what is left is remains to calculate the derivative of this third root. So now let's consider it separately. Third root x squared minus 2x derivative. And here I want to apply, of course I can use the generalized power rule because one way to write that third root of something is the same as something to the power 1/3 and generalized power rule. Some function u. All right, this is one way to do that. But let's again practice the chain rule because this is one of the most complicated. Other chain rule. And so my first function g of x, which is I also denoted by u, is x squared minus 2x, right? And my f of x will be, some sense I still need to generalize power rule, but so and that will be third root of x. Then composition of f and g point x is f of g of x. This is just the definition of the composition of two functions. And this is again f evaluated at x squared minus 2x, which is third root, x squared minus 2x. So indeed, the function that we want to differentiate. Okay, so we can apply, and if we call this root by y, so y is third root of x squared minus 2x, then by the chain rule, dy over dx will be df as a value of u divided by du times du over dx. So in some sense, it's better also to write down it in the following way, because now what you need to do, you need to calculate f evaluated f of u will be third root of u, right? Here. So what will be then df over du? It is the derivative of such function, which is the same as u to the power 1/3. And again, in some sense, it is generalized power rule. Generalized power rule. So it gives me 1/3 u to the power 1/3 minus 1 times, and that's it, because I'm differentiated not with respect to dx, right? There is to be the big difference. I'm not considering here u as a function of x. I just consider u itself. So it's a function of u, and I differentiate with respect to u. There is no x here so far. X appears in the next multiplier, in the next factor. While here, no x. Okay, so I obtain this, or I can write it the following way. So it's 1/3 u to the power minus 2/3. Okay. Okay, and the last step is to calculate du over dx, which is the derivative of u, which is x squared minus 2x. And this is again just polynomial, so it's 2x minus 2. And finally, what I need to write. So dy over dx will be thus df over du, which is 1/3 u to the power minus 2/3 times du over dx, which is 2x minus 2. But now I want everything be expressed in terms of x, so I need to come back to x, and my u, recall that u is equal to x squared minus 2x. And that's what I'll plug here. So it's 1/3 x squared minus 2x to the power minus 2/3 times 2x minus 2. Or you can write it down in the following way. So it's 2x minus 2 divided by 3. And then I have x squared minus 2x to the power 2 and third root of that. Maybe it doesn't look better than this one, but this is another way to write it down. Okay. Of course, you will obtain the same answer if you use the generalized power rule. But again, what I wanted to practice the chain rule.